All right, let's get into it. Today, we're basically becoming digital detectives. You ever wonder how a computer sifts through this massive ocean of data to find just one thing? Well, we're going to crack that case wide open, and our main tool is going to be C++. I mean, really think about it for a second. You go on your favorite social media site or check your bank account, and boom, your info is there instantly. It feels like magic, right? But it's not. It's all down to some seriously clever algorithms. So the big question is, how on earth do they pull that off? Okay, so first things first. Before we can find a clue, we need to know how the evidence room is organized, right? In the world of programming, our go-to for organization is the array. And the best way to think about an array? It's like a super neat, perfectly organized digital filing cabinet. Now, this filing cabinet has a couple of really strict rules. Rule number one, everything inside has to be the same type of thing. So you can have a cabinet of just numbers or just text, but you can't mix them up. And rule number two is they're all stored contiguously. Fancy word, but all it means is they're sitting right next to each other in the computer's memory, no empty space between them. It's all one neat, continuous block. And that structure is super important. Every single drawer in our cabinet gets a number, which we call an index. But here's the classic programmer thing you just have to drill into your head. Computers start counting from 0. Not 1, but 0. So if you've got 5 drawers, they're not numbered 1 to 5. They're 0, 1, 2, 3, and 4. The last drawer is always the total number of items minus 1. Gotta remember that. Okay, our filing cabinet is set up. Now it's time to actually find something. Let's start with our first detective technique. It's the most obvious, the most straightforward approach. You could call it the brute force method. So, you've got this cabinet full of files. How do you find one specific file inside? If you've got no other clues, no special system, what's the one way you can be absolutely sure you'll find it? Yep, you guessed it. You just start at the very first drawer and check every single one. That, my friends, is a linear search. It's simple, it's methodical, and hey, it'll always get the job done, eventually. So the plan is dead simple. You pop open drawer 0. Is this what I'm looking for? Nope. Okay, on to drawer 1. Is this it? Still no. And you just keep doing that, drawer by drawer, until you either shout, aha, found it, or you get to the end of the cabinet and realize it wasn't there in the first place. Now, in the world of computer science, we have a way to measure how efficient, or, how slow this is. We call it time complexity. For a linear search, its complexity is O of n, which we say as big O of n. Don't let the fancy terms scare you. All it means is that in the worst possible case, if you have n things to search through, it might take you, well, n checks. Simple as that. And right here is where our trusty brute force method just falls flat on its face. I mean, if you're looking through a handful of files, no big deal. But what if you have a million files? A database with a million users? You could end up making a million checks. That's not just slow, that's completely impractical. There has to be a smarter way to do this. And there is. This brings us to the real secret weapon in any digital detective's toolkit. This is where we stop working harder and start working smarter. The strategy is called divide and conquer, and the algorithm that uses it is the incredibly powerful binary search. So, let me ask you a question, because this one question changes the entire game. What if our files weren't just in the cabinet? What if they were sorted? Alphabetically, or from smallest to largest number? How would that change how we search? This right here is the catch. It's the one, single, non-negotiable rule. For any of this binary search magic to work, your data, your array, has to be sorted beforehand. That's the price of admission. It's the trade-off you make for getting that incredible speed. So how does it work? Well, true to its divide and conquer name, binary search takes your whole collection of files and just chops it in half. Instead of painstakingly checking one file at a time, you get to throw away half of your search area in one single move. It's brilliant. The logic is just so elegant. You don't start at the beginning. No, you jump straight to the exact middle of the cabinet. You pull out that middle file and ask, is this it? If it is, awesome, you're done. But if it's not, you ask another question. Is the file I'm looking for alphabetically before or after this one? Let's say you're looking for Johnson, and the middle file is Miller. Well, J comes before M, right? So you instantly know your file has to be in the first half. You can completely, totally ignore the entire second half of the cabinet. Boom, half your work is gone in a single check. And then you just do it again. You take that remaining half, find the middle of it, and make the same decision. You keep chopping the problem in half over and over. With every single step, your search area gets exponentially smaller. It's just so efficient. So let's talk time complexity again. This is where your jaw might drop. It's not O of n anymore. It's O of log n. So what does that actually mean? Okay, let's go back to our 1 million items. A linear search could take up to 1 million steps. Binary search, in the worst case scenario, it will take about 20 steps. Yeah, you heard me right, 20. That's not just a little better, that is a complete and utter game changer. So let's put them head to head. Linear search, simple, easy, works on unsorted stuff, but man, is it slow on big data. Then you have binary search, incredibly, ridiculously fast, but it has that one big requirement. Your data has to be sorted first. And let me tell you, for almost any real-world application where you're doing a lot of searching, making sure your data is sorted is a price you're more than willing to pay for that kind of speed. All right, for this last part, let's get a little more technical. We've been using this filing cabinet idea, and it's a great way to think about it. But what's actually happening deep down in the computer's memory? Let's pop the hood for a minute and see what's really going on. This is a core idea in C++ that you've got to understand about arrays. When you make an array, say int my number's 10, that name, my numbers, isn't the whole pile of numbers. Not at all. That name is really just a constant pointer. It's a signpost that points to one single thing, the exact memory address of the very first item in that array. So, what's a pointer? It's just a special kind of variable. Its entire job in life is to hold a memory address. That's it. A good way to think of it is like a sticky note. The sticky note doesn't have the full report written on it. It just says the report is in filing cabinet B, drawer 3. It tells you where to find the real information. And the name of an array is basically a permanent sticky note that's always pointing to drawer 0. And this is why these two ways of writing things are really just two sides of the same coin. When we write array I with the square brackets, that's what we call syntactic sugar. It's nice and easy for us humans to read. But what the computer is actually doing under the hood is pointer math. It's doing star array plus I, which means go to the starting address array, hop forward I spaces in memory, and then give me the value that's stored right there. They do the exact same thing. And this explains a behavior that trips up a lot of new C++ programmers. When you pass an array into a function, you aren't making a copy of the whole thing. Imagine copying a 1,000,000-item filing cabinet every time. That would be so slow. Instead, you're just passing that little sticky note, that starting address. That's why if the function changes something in the original array is changed too, because there's only one filing cabinet. Everyone's just using the same address to find it. So think about what we just saw. Just by changing our strategy from a brute force one-by-one check to a clever divide and conquer approach, the performance difference wasn't just big, it was astronomical. It kind of makes you wonder, right? What other beautiful, elegant solutions like this are hiding just under the surface of the software and apps we use every single day?